Good afternoon. Today's topic sounds a bit provocative: hacking the 1C structure. But let me clarify right away. This is not about illegal hacking and not about accessing someone else's data. We are talking about a technical analysis of your own or a test database in order to understand how 1C and BAS are actually structured, how this data can be imported, how to connect to it, what nuances appear, and, most importantly, why it makes no sense to build a so-called transparent migration on old 1C/BAS databases and configurations. Very often, people suggest the following idea. Let's not move the data into a new structure. Let's simply connect the new system to the old 1C or BAS database and keep working. At first glance, it sounds beautiful, fast, cheap, and painless. But in practice, it is like installing a Tesla screen into an old Zaporozhets and saying, "Now we have an electric car." No, you do not. Because the problem is not only in the interface. The problem is in the database structure itself, in the data types, in the old architectural decisions, in the configurations, in partner modifications, and in the baggage that has been dragging along since the 1990s. Today, I will show different variations of 1C and BAS databases. BAS is essentially the same 1C, only with a different name and a different icon. The name changed, the icon changed, but the same technological legacy remained inside. To begin, let's look at the architecture of different generations of 1C. 1C appeared back in the 1990s. First, there was a DOS version, then a Windows version. There was also an old 1C6, which almost nobody sees in real work anymore. The more popular versions became 1C 7.5, 1C 7.7, and then 8.1, 8.2, 8.3, and later versions. If we talk about BAS, it is essentially the 1C 8.3 line renamed after sanctions against 1C. Externally, it was presented as a different product, but technologically, it is a continuation of the same platform. The processes, logic, and approaches are very similar. In essence, they changed the signboard, but not the foundation. And the foundation is exactly where things get interesting. Now we are looking at 1C 7.7. This version clearly shows where many of the problems come from. 1C 7.7 worked with DBF files. This is an old file-based database format, which was normal for its time, but for a modern ERP system, it is already technological archaeology. Yes, it may seem that almost nobody works with 1C 7.7 anymore, but in practice, many companies still have such databases. At some point, they started accounting in 1C 7.7, then got used to it, then accumulated modifications, then became afraid to migrate because they did not want to lose information. And so the database lives on for years. It is like an old refrigerator at a country house. It buzzes, leaks, freezes only one shelf, but it would be a shame to throw it away. It still works. Here we are launching 1C 7.7. By the appearance alone, you can already distinguish the generation of 1C. Here we see an old interface, old menus, old windows. But we are not interested only in the interface. The interface can be redrawn. Buttons can be made prettier. Icons can be replaced. But if inside there is an old database structure, old data types, and old principles of storing information, that is already a serious problem. On the screen, we see that the database asks for access. In old file-based solutions, service information, rights, users, and technical settings were organized much more simply than in modern systems. For this demonstration, the important part is not exactly how access can be bypassed in a test database, but the fact itself. The old file-based architecture had very primitive mechanisms for storing service information. In a modern ERP system, security must be a proper model of roles, rights, audit, logging, and access control. But in old file-based approaches, many things lived in folders, service files, and technical agreements. And here a logical question appears. If such fundamental things were dragged from the past for so long, what else remained from those times? Scalability? Integrations, data types, table structure, update approaches, performance? Because technical debt rarely lives in just one place. If in one corner of a building you find wiring from 1978, twisted with blue electrical tape and labeled "Do Not Touch, it works," you should not assume that in another corner you have a Google data center. Next, we see the database folder. DBF files are located here. DBF files contain the actual data. Index files may be located next to them. If indexes are damaged, the database must be launched in exclusive mode and re-indexed. So already at this level, we see the old logic. A file-based database, separate indexes, exclusive mode, old encodings, old limitations. This is not just a historical detail. A large part of the later architectural legacy of 1C grew out of this logic. Later, new versions appeared. SQL databases appeared. BAS appeared. Newer interfaces appeared. But some approaches continued to trail behind. That is why when someone says, let's just leave the old database as it is and build a new ERP on top of it, you need to understand, as it is not a modern ERP. As it is a museum of technical compromises. Next, we enter user mode. Here we see the usual interface: menus, documents, directories, reports. A user can work, enter documents, open directories, and generate reports. But for migration, this is not enough at all. The user sees the menu, but we need to understand how this data is stored inside, where directories physically lie, where documents are stored, where tabular sections are stored, where registers are stored, where enumerations are stored, where service fields are, where the real business data is, and where the technical noise of the platform is. So we move to the configurator. In 1C, there is always a regular launch mode and a configurator mode. The configurator is the place where we can see the structure of the applied solution: directories, documents, document journals, enumerations, reports, data processors, charts of accounts, registers, calendars, and other objects. In 1C 7.7, the configurator looks older. In 1C8, it became more advanced, but the idea remained the same. The configurator shows the logical structure of the application. Here we open the configuration and see the objects. These objects are important because they are exactly what we need for data migration. When we open an object, we can see its properties, attributes, data types, field length, forms, and modules. In 1C8, there is a similar object inspector. It just looks different. Now we move through the structure and see directories, documents, and document journals. These are the basic entities of an accounting system. Directories are, for example, banks, counterparties, products, warehouses, employees. In the configurator, we can expand a directory and see its attributes, field names, value types, lengths, forms, and modules. Even in 1C 7.7, there were already quite a lot of capabilities. You could edit forms, open modules, see program code, configure groups, properties, and attributes. But it is important to understand the difference here. What we see in the configurator is the logical level. How it is stored in the physical database is a different story. For the user, it may be a bank's directory, but physically, in DBF or SQL, it may be a table with a technical name that means nothing to a human. And this is where the problem of transparent migration begins. If a new system simply works on top of the old 1C database, it inherits not only the data, but also this old, opaque structure: technical names, service fields, specific data types, configuration-specific features, and partner modifications. This is not modernization. This is technical hostage-taking. Next, let's look at documents. In 1C, a document is not just one record. It has a document header. There is always a number, a date, an organization, and there may be notes and other standard fields. Some of these fields exist as part of the document entity itself and are not always displayed in the structure the way a developer accustomed to a normal SQL model would expect. In addition to the header, a document may have one or several tabular sections. For example, in a bank statement, invoice, or bill, there is a document header and there are rows. One document, many rows. At the database level, this is a one-to-many relationship. If there are several tabular sections, then there will be several related structures. For migration, this is critical. You cannot simply take a document as one row. You need to correctly extract the header, correctly extract the tabular sections, restore the relationships, preserve the order, understand the service fields, and avoid confusing real business data with technical platform information. And that is still a more or less typical case. Now imagine a real client database where a partner once added custom fields, changed a document, wrote an additional data processor, created a separate register. Then another partner changed something. Then the accountant said, "Do not touch it, it works," and all of it has been living for 15 years. And after that, someone seriously says, let's build a new ERP directly on top of this structure. That is not architecture. That is a technical salad. Next, we look at document journals. A document journal is essentially a list of documents, a convenient grouping for the user. But for migration, what matters is not how the journal looks in the menu, but which documents stand behind it, which tables are used, how they are connected, and where the data is stored. After that, we move to enumerations. Enumerations are a very important topic. In a regular relational database, many such things would logically be stored in separate tables: product type, operation type, status, warehouse type. But in 1C, some of these values may live not as a full-fledged table, but as an element of the configuration. For example, we see types of inventory items: product, service, packaging, finished product, material, construction material, fuel, and other options. For the user, this is just a list of values. But when we extract data directly, we may see only an identifier, not the human-readable value. And then the question appears, where do we get the decoding? In the table? In the configuration? In a module? In XML? In the head of a programmer who left the company 12 years ago? That is why the old structure cannot be dragged along as a foundation. It is not a normal universal model. It is a set of decisions made by a specific platform, a specific configuration, and specific modifications. In K2 ERP, we usually implement such things through proper directories or clear data models, so that later we can work with SQL queries, integrations, analytics, APIs, and reports. In 1C, part of the logic may be hidden in the configuration, and that is inconvenient for migration, analytics, and integrations. Next, we see reports. In 1C7.7, reports may have sections, forms, and program code that inserts data into the required places. These are essentially document and regulated report templates, where program code defines which rows to output, where to take data from, and which sections to repeat. Here, we also see that forms may be in Russian, Ukrainian, or different languages. This is a separate part of the configuration and part of the business logic may be not in tables but in forms, modules, and reports. So the database is only part of the truth. The second part lives in the configuration. The third part is in the program code. The fourth is in data processors. The fifth is in partner modifications. And then someone suggests leaving all this as the foundation of a new system. That is like building a business center on an old barn, where every wall was added by a different craftsman, and instead of blueprints, there is a note saying, "Do not touch, it works." Next, we move to data processors. A data processor is program code that does something with data: exports, imports, recalculates, generates reports, modifies records. In 1C8, data processors are also actively used. After that, we look at the chart of accounts. In a normal system, the chart of accounts could be viewed as a table. In 1C, it is a separate platform entity. There are chart of accounts attributes. There are the values themselves in the database. There may be several charts of accounts, types of subconto, operations, and postings. Next, we see registers. In 1C7.7, registers were still weaker. The word register exists there, but we do not yet see the full power of accumulation registers, information registers, accounting registers, and calculation registers as in 1C8. In 1C8 and BAS, registers are already used very actively: balances, turnovers, movements, analytics. But for migration, one thing is important: the business does not need the old 1C mechanisms themselves. The business needs the result: balances, turnovers, documents, postings, settlements, history, analytics. So we migrate the meaning of the data, not the old construction, because if we migrate the old construction, we migrate all the technical debt along with it. Next, we talk about XML. When data is exported to XML, we see approximately the same object structure as in the configuration. XML is the serialization of these objects. It may contain both the descriptive part and the data itself. XML works well for small databases. It is convenient because you can get the structure and the data in one format. But XML is not always suitable. When the database is large, XML grows very very quickly. It contains many tags, a lot of service information, and a lot of redundancy. Even if the value is just one digit, XML will add an opening tag, a closing tag, structure, nesting. As a result, the data volume increases, speed drops, and processing becomes more complicated. For small databases, fine. For large databases, often painful. If your database is 500 gigabytes or a terabyte, XML can turn into a suitcase without a handle, hard to carry, but a shame to throw away. That is why for large projects, it is better to work directly with the database, but directly as a data source, not as the foundation of a new ERP. Direct access gives important advantages. We can copy not everything, but only what is needed. We can load data in the required order. We can compare the old database with K2 ERP. We can transfer the delta, only what has changed since the previous load. If the database is SQL-based, we can take data in batches, not a million rows at once, but in parts. For example, from the first row to the 1,000th, then from the 1,000th to the 2,000th, and so on. We can get the row count, move in batches, and control the process. For large data volumes, this is much more efficient. But once again, direct access is needed to extract the data, not so that the new ERP lives forever on the old 1C structure. Now we look at the physical database files. On the screen, we see strange file and table names. Why is that? 1C is a very old system. It appeared in the 1990s when there were DBF files, FAT16, and file name limitations, 8 characters before the dot and 3 characters after it. It was impossible to fit names like bank statements, counterparties, product catalog, or storage locations into such limits. So historically, 1C took the path of technical identifiers. Tables were named not in a way that humans could understand, but in a way that fit into old limitations. And the most interesting part is this. Later, SQL databases appeared, where such limitations no longer existed, but the tradition of gibberish remained. It is like installing running water for a person, but they still go to the well with buckets because that is how it has always been done. This shows the level of architectural refactoring. If over decades even fundamental things, table names, data types, storage structure, were not brought to a normal state, why should we believe that the other parts of the system are perfectly modern? We should not believe it. We should look under the hood. Next, we open DBF files. They can be opened in different ways, sometimes even in Excel. But this is a dangerous method for a production database because Excel may save something incorrectly, change the format, or damage the file. So you should work with a copy and be very careful. In the DBF editor, we see fields, data types, and records. Some names are more or less understandable, and in other places, technical gibberish begins. SP, numeric identifiers, service fields. Here we can see old data types, fixed-length character fields, numeric fields, dates. Strings may be padded with spaces. Dates may be stored in a specific way. Dates are a separate story. In old systems, there was the year 2000 problem, and 1C historically used its own approaches to dates. In the 8th version, you may also encounter date recalculations, for example, when you need to subtract added years. And then this appears in SQL queries, BI reports, and data conversion. So we see that 1C carries a large legacy of its old decisions, and this legacy now comes back to bite. Why did they not refactor it? Because deeply rebuilding the foundation has become very difficult. Historically, 1C developed mostly the platform and the development tool, while applied configurations were massively created by partners. Each configuration could be modified for a specific client. If you now radically change the table structure, data types, storage principles, and mappings, a huge number of configurations, modifications, integrations, and partner solutions may break. So the old baggage was not removed. It was preserved. Then new layers were added on top. Then more layers. Then this was called development. But in reality, a significant part of this development is old technical debt covered with new menus, new names, and new presentations. In this sense, BAS looks like a modern program, but inside it carries the legacy of a system from the 1990s. Limitations from the previous century still exist in the structure, data types, table names, and approaches to storing information. We have seen the data. Now we need to understand what each table means. We are not going to work with gibberish blindly. We need to look at the configurator, open the actual application, view the real directory, compare the data with physical tables, and map all of this to K2 ERP models. In 1C 7.7, this can be decoded through metadata files. There is a file that describes the structure, which logical objects correspond to which physical tables, which fields exist, and which data types are used. Here we see system tables. For example, the user table has an understandable name. System tables are sometimes named normally, but configuration tables often have technical names. Next, we see constants. Constants are also placed in a separate table. They may have different types of values: string, date, number, service values. There may be many constants, and they are used for settings. Next, we move to a specific directory, for example, banks. In the configurator, we see the logical name, and in the metadata, we see the physical table. For example, the table may have a name like SC327, and the fields may be SP330, SP2499, and other technical identifiers. For a human, this is inconvenient. For migration, this means that a mapping must be built. Logical entity, physical table, physical field, data type, K2 ERP model, K2 ERP field. And this is where it becomes clear why transparent migration on the old database is a trap. If we simply leave the old database, the new system will be forced to live forever with SC327, SP330, binary, hashes, date recalculations, different configurations, and partner modifications. This is not a new ERP. This is a new interface to an old problem. In 1C 7 setting, we must also remember enumerations. They do not always live in the database as tables, so if we extract data directly, we may see an identifier but not understand its human-readable value. To load this correctly, we need to additionally parse the configuration or other sources of structure. The essence of the approach is this: we parse the structure description, get the table name, field name, data type, directory, or document structure, and after that, we can access the required table directly. Then all of this must be mapped to K2 ERP. K2 ERP has its own models, physical and logical structure. We can take the 1C structure, the K2 ERP structure, data examples, XML, table descriptions, and use artificial intelligence for the initial mapping. It can suggest rules for the replicator, which field to take from where to put it, how to convert types. After that, a specialist checks everything, corrects mistakes, further trains the system, and starts the migration. And this is important because the task is not to migrate one database manually. The task is much larger, to replace hundreds of thousands of 1C and BAS databases in Ukraine. A robot, a replicator, artificial intelligence, and specialist control must work here. The robot needs to be trained. Its mistakes must be corrected, but overall, this is the right direction. Now we finish with 1C 7.7 and pay attention to one more point: encoding. Old databases may have DOS encodings, Cyrillic, problems with folder names, question marks instead of characters. If names are in Ukrainian or Cyrillic, old tools may process them poorly. This again shows that we are not dealing with a modern, clean architecture, but with historical layers stacked on top of each other. Next, we open another 1C 7.7 configuration, a more complete one. Here, there are more menus, directories, documents, constants, and these examples clearly show that different configurations may be organized differently. For example, we search for warehouses. In the menu, the user sees warehouses, but in the structure, this may not be called warehouses, but storage locations. Or a warehouse may be linked to a company, store, warehouse type, enumeration, or another entity. This is where the main problem of transparent migration becomes visible. There is no single universal 1C structure. There are different configurations, different versions, different modifications, different names, different logic. What is called a warehouse in one database may be a storage location in another, a department in a third, a company attribute in a fourth, and a tricky partner modification in a fifth. We search for warehouses and do not find it. We look through code, forms, modules, enumerations. Then we find storage locations and understand that this is actually the warehouse in this configuration. So in the menu, it is one thing, in the configuration, it is another, and in the physical table, it is a third thing. And after that, someone says, let's make the new ERP work transparently with this structure. Seriously? This is not transparent migration. This is an attempt to tame a zoo, and every database is a separate animal. One bites, another spits, the third one is standard but somehow has a dragon's tail. We open the physical table, for example SC129, and see the main warehouse and other storage locations there. So we confirm, yes, in the menu it is warehouses, in the configuration it is storage locations, and physically it is a technical table. This is exactly how migration must be done. Find the meaning, not blindly copy the old structure. We take the data, we do not take the old chaos. Next, we move to 1C8 and BAS. In 1C8, there are two interface options, the FIC client and the fin client. When we see old gray buttons and the classic interface, this is the FIC client. The fin client may look more modern, more colorful, with different forms, but what matters is not only how the interface looks, but how the architecture works. In 1C8, there are two database storage options, file-based and SQL-based. For migration, it is much more convenient to work with a SQL database because we can connect directly, write queries, select data in batches, and analyze tables. The file-based option is more complicated. There is also an internal database there, but it is significantly less convenient for industrial-scale migration. On the screen, we see a SQL database. And what do we see at the table level? The same tradition of gibberish. Tables, fields, registers, documents, tabular sections. Everything is named with technical identifiers. There are already other abbreviations, other structures, more entities, but the principle is the same. Without decoding, it is difficult for a human to understand what is stored where. For example, documents have their own tables, tabular sections have their own tables, registers have their own tables. Fields may not be simple data types, but binary, B16, internal identifiers, hashes, references. And when you extract this with SQL queries, you need to convert types, decode references, adjust dates, and map identifiers. This is the answer to why it makes no sense to use 1C/BAS databases as the foundation of a new system. At the structural level, it is old, cluttered junk. There is gibberish in the names, complex data types, binary values, hashes, strange dates, recalculations, technical identifiers, service tables, registers, tabular sections, configuration links. Instead of simply opening a clear table and seeing clear data, we get a technical quest. Find the table, find the field, decode the type, subtract 2,000 years from the date, convert binary, find the enumeration hash. Do not confuse the register. Do not forget the tabular section. This is not architecture for the future. This is an escape room for a programmer. Next, we see an example of connecting to Microsoft SQL Server. In SQL Server, you can connect to a database, open tables, and view the structure. This is useful for analysis and migration, but when we start building real SQL queries to a 1C database, especially for Power BI or analytics, the problem quickly becomes visible. Queries become long and complex with aliases, type conversions, date recalculations, joins to technical tables, and enumeration hashes. For example, to get a normal date, you need to perform a conversion. In 1C8, you may encounter logic where added years must be subtracted. So even a date, a basic data type, requires special processing. For enumerations, there may be a hash that must be compared with a specific value from the configuration. So instead of a normal human-readable value, we have a technical identifier. As a result, the SQL query grows into many lines. It is difficult to read, difficult to maintain, difficult to modify. If you need to add a new field or change the logic, it is very easy to make a mistake in a technical identifier or type conversion. And such queries can also be slow, especially on large databases, 500 gigabytes, half a terabyte. Servers may collapse under such queries because the structure was not designed for convenient direct analytics. On the screen, we see examples of such SQL queries for BI. They work, but at what cost? Huge queries, type conversions, technical names, many relationships, additional processing in Power BI. If SQL suddenly needs to be corrected, this is no longer normal support. This is excavation work. You need to check types, dates, fields, hashes, mappings again. This is why it makes no sense to build a new system on top of the old 1C/BAS structure. Because you are migrating not only the data, you are migrating pain, slowness, technical debt, and dependence on old decisions. Next, we move to the 1C8 thick client. In 1C8, we can no longer simply open a metadata text file, as in 1C7.7, and easily read everything. The structure is stored in a more complex way. Special data processors are used to obtain the structure. There are data processors for the thick client and data processors for the thin client. And this also matters because the thick and thin clients work differently. The thick client was historically more oriented toward more direct work with the database. The thin client works through the application server. The client sends a request to the server accesses the database, then the result is returned to the client. From a security point of view, the thin client is more correct because the client does not have direct access to SQL. But historically, many 1C solutions worked through RDP because normal work over the internet for 1C was often problematic. The thick client over the internet is a dangerous idea, so it was usually hidden behind RDP. The thin client was also often run through RDP because performance and convenience did not always meet expectations. This is another sign of old architectural legacy. Instead of a normal web architecture, business often lives on RDP, thick clients, thin clients, an application server, and compromises. K2 ERP has a different approach. Modern web architecture, APIs, clear models, integrations, normal work through a browser, and modern clients. Next, we open the 1C8 configurator. It is much more powerful than in 7.7. There are more entities, more subsystems, common modules, roles, directories, documents, registers. Here we already have accumulation registers, information registers, accounting registers, calculation registers. In 1C7.7, registers were weak, but in 1C8 they became the foundation of work. The idea of registers in 1C is that the programmer does not always need to manually think about indexes because the platform builds indexes based on register dimensions. This provides a certain convenience, but for migration, this is again a complex layer. The business does not need the register itself as a 1C object. The business needs balances, turnovers, movements, postings, settlements, analytics. So we need to understand the registers, extract the meaning from them, and put it into a normal K2 ERP model. The same story applies to directories, constants, and enumerations. Everything that existed in the old architecture moved forward. It simply became more complicated. The names may now be longer than 8 characters, but the gibberish remained. Next, we launch a data processor for the thick client. The data processor shows the configuration structure, logical entities, physical table names, fields, data types, mappings. This is very useful for the replicator. We can see which logical entity corresponds to which physical table, which fields it has, and which types need to be processed. For example, we search for a register. We see the physical table. We open it through SQL or DB Viewer. We get the data, but then we again see problems, encoding, binary identifiers, references, types that need to be converted. REF fields mean links to other tables. To get a human-readable result, you need to make joins, convert types, and decode references. So, in principle, everything can be extracted. But the question is, at what cost? For migration, yes, it is necessary. For permanent operation of a new ERP on top of this structure, no. Next, we move to the thin client. The principle is the same, only the data processor is different. It also shows the configuration structure, table names, and fields. In some configurations, the thick client and thin client may exist at the same time. This looks quite strange, but for 1C/BAS it is normal. The old is not removed, the new is added on top, and historical layers live together. This is very characteristic of the entire 1C and BAS ecosystem. They did not remove the old baggage. They often simply added new layers on top. Why? Because historically, 1C developed mostly the platform and the tool, while applied configurations were massively created by partners. If you now deeply change the database structure, data types, storage principles, or mappings, a huge number of configurations, modifications, integrations, and partner solutions may break. That is why they have been dragging this baggage along for decades, not because it is a brilliant architecture, but because this knot is already scary to untangle. But But that does not make life easier for businesses. Business should not be held hostage by old technical debt. Now, the main conclusion. Why does it make no sense to build a transparent migration from 1C or BAS on the basis of existing databases and configurations? First, the structure is old. It carries the legacy of DBF, DOS, FAT16, old limitations, technical identifiers, and decisions from the 1990s. Second, the structure is bad as the foundation for a modern ERP. It can be a data source, but not the architecture of the future system. Third, the structure differs across configurations. Accounting, trade, payroll, management accounting, industry-specific solutions, everything may differ. Fourth, the structure is also modified by partners. This means every database can be a separate story, a separate zoo, a separate archaeological monument. Fifth, 1C and BAS themselves cannot easily refactor this because their ecosystem is built on the platform, configurations, and partner modifications. Change the foundation and the extensions may collapse. So transparent migration on the old structure is not modernization, it is a trap. It may look as if you are moving to a new system, but in reality, you remain tied to the old database, old logic, old tables, old data types, old registers, old hashes, old dates, and old problems. The correct approach is different. We take the old 1C or BAS database as a data source. We analyze its structure. We extract directories, documents, balances, postings, registers, analytics. We build a mapping to K2 ERP. We transfer the data into a new, proper model. We verify the result, and only after that do we launch the business on a modern Ukrainian ERP system. In other words, we take from 1C what belongs to the business, data, history, documents, analytics, but we do not take the old architectural mold. Because business needs its data, not a museum of technical debt. This is exactly why K2 ERP is being created. We are not building a new wrapper over old Russian technological legacy. We are moving the data into a new architecture. And this is the fundamental difference between a real replacement of 1C/BAS and yet another imitation of migration. So today we are hacking the 1C structure, not in order to break it. We are doing it to show that the old structure must be understood, decoded, and used only as a data source. The future of Ukrainian business should no longer be built on 1C and BAS, but on a modern, clear, and independent ERP platform. Thank you for your attention.